What if your code could automatically detect hidden bugs before they cause a security breach? Imagine catching a divide by zero error or finding a SQL injection attack just thanks to AI. Today, we're talking about how LLMs and data flow analysis can help software engineers do just that. Hey everyone, welcome back. Today we're going to dive into a research paper that takes a big step forward into what the future of software engineering might be. It explores how large language models, like the ones you're probably familiar with, could really change the kinds of bugs we can see in the way we are able to find security vulnerabilities in our code. So we're talking about things like automating the detection of things like divide by zero and SQL injection attacks. This is done with something called Dataflow analysis, and that might sound a little bit abstract, but we're going to walk through it and explain what that is. This is going to get really interesting for anyone if you're writing code or dealing with software security, because we're going to see how the models that are coming out today could one day change the way that you're coding to make it much more obvious when you have a security vulnerability. So let's jump right into it. Great. Done. Okay. The basic idea is we're doing code flow analysis with LLMs. So let's learn a little bit about what code flow analysis is. So here we have a program, a bit of software, and we want to detect certain classes of bugs in the software. So here we're looking, in this specific example, we're looking for something called DBZ. What is that? Oh no, new acronym. No, not scary. DBZ, divide by zero. So we're just trying to detect a divide by zero bug in this program. And we're trying to write essentially another program that can take this program as an argument and return whether or not it thinks there could be a divide by zero issue in the code. Code flow analysis. Looking for certain kinds of bugs in code, like divide by zero, aka DBZ. If you're cool, then you can call it a DBZ bug. And there are some other kinds of examples they give here of problems that you can solve with code flow analysis. So I think in this particular paper, they look at three kinds of example, and I think maybe one or two more later on. But the three they mentioned are divide by zero, cross-site scripting, aka XSS, or OS command injection, which they call OSCI. Now, you don't really need to understand what all of those are if those are unfamiliar to you, but the basic idea with all of them is that, or what can happen with all these kinds of bugs is that you can if you put the wrong data in the wrong place, you can cause an error. So here's an example of a divide by zero bug, and the critical thing that it has in common with these other things, XSS, cross-site scripting, and OS command injection, is there's data that can come in from an outside source. So from here, in an example, it comes in on a command line argument. You can imagine also something that might come in as an API argument if you're building a web server, or like something that could come in from an interactive prompt, if you have like some sort of CLI app you're building. So it comes in to the program from somewhere else. So you might say there's a source here. And then it's perfectly fine to use that argument, no problem, until you try to divide by it. If you had that line of code here, you could immediately tell, oh, there's going to be an error. Not too hard to analyze. It's not too hard to visually analyze that, read that, and figure out what's going on. Because you can see, okay, X is on the bottom. So it's on the bottom. It potentially is coming in from a source that we don't control. It potentially could be zero, so we have to be careful about doing this kind of math. Now, this can also get more complicated, which you can see in this code. This can also get a little more complicated, as you can see in the code here, where you have like X coming in, but then you can see here, okay, X turns into this variable called Z, and then we call a method here on Z, where Z is now called B, and B is in the denominator. And then, now potentially B, which really originally is the same as this X, potentially could be 0. But we're safe because we have this if statement here. So that analysis is much harder for us to do. And that's the problem we're trying to solve with code flow analysis, is how can you tell that, first of all, this B is the same as this X? How can you recognize this potentially as a problem? And then also, how can you recognize that the if statement will save you? So there are 3 steps involved in this. And at least in this paper, this is how they do it. 3 steps. First, identify sources and sinks. So that's the first bit of terminology. So we can take a quick look at that here, and you can see they annotated it in their code. So what's a source? A source is something inbound, some data that came from a place we don't control, like the user, like we talked about. What's a sink? So a sink, it depends on the kind of bug we're looking at. So if it's a divide by 0 bug that we're trying to detect for, then a sink specifically means, okay, anytime you have a denominator on the right, a denominator, anytime you're doing division, potentially that's a sink. If we were looking at a different kind of bug, if we were looking at like OS command injection, like accidental, like putting bad data on the operating system, instead of looking at division, we would look at something else, like calling out to a system command, and those would be our sinks. So the sink depends on what we're trying to look for, which kind of bug we're trying to detect. So that's the first thing. Just identify all the sources and all the sinks. The next one, Dataflow summarization, which essentially means if you ignore for a moment the sort of semantics about like control flow stuff, and you just take a look at like which variables are connected to which other variables, that's what they call Dataflow summarization. So the idea, you need some algorithm to be able to detect that this B is the same as this X. So this is Dataflow summarization. What is it? What does that mean? Recognize that B is the same as X. All right, I'm going to pause. The final step for analyzing data flow is what they call path feasibility validation. So while we did successfully recognize that X and B here are the same variable, so this source is connected to this sink, in practice, we don't have to worry about it because there's this conditional if statement that prevents this line of code from ever actually executing. So we don't have to worry about it. Or very specifically, it prevents it from executing under the condition where B is 0, which is the condition we're worried about. So that one they call path validation. Essentially checking the if statements and control flow structures on the data flow paths. So that's it. So 3 steps: source sink identification, data flow summarization, and path validation. But before we really dig into the details about how they do that, which is kind of cool, I'm going to just like cheat a little bit. Let's skip to the results. Let's skip to how good is this? And then we can rewind and look back and dive a little more into how they did it. Okay, so here's some fun facts here. There's some things they pointed out that I thought were really interesting. Evaluation. First interesting thing, don't be afraid to spend money. The testing of their algorithm costs $1,600. So prices have probably come down a little bit since then, but they're really pushing a lot of data to be able to evaluate this. And you can see that they must have just chewed up a significant number of tokens to get this all to work. And okay, they have a couple test suites. The first one's called the Juliet test suite. A benchmark, so it's a common benchmark for that happens to use these examples: DBZ, XSS, OSCI. Okay, and so the three kinds of errors: DBZ, XSS, and OSCI. They talk a little bit about the subtle differences between them. DBZ has very strict control flow because you only have a bug if it's exactly 0. And then you can see the sinks are a little different, of course, depending on the different forms. And in this data set, there are about, 2,000, about 3,000 total bugs. The other one's called Taint Bench, which has 39 real-world applications. Each one has specific sources and sinks that are customized to its unique functionality. And I believe what they're saying with this is that this goes beyond, so 39 real-world applications, going beyond the 3 bugs mentioned above, like leaking your personal information, for example. And this is sort of the magic of LLMs and why they're excited about this whole thing, is that, you can imagine maybe some automated system can do a reasonable job for these kinds of bugs, but it involves some bespoke work for each kind of bug, writing a custom sink detector and custom source detector. And that work can kind of add up, and there are like different subtleties and constraints with the different kinds of bugs. When you're looking in the real world, there are many other kinds of bugs that could happen, like leaking your personal information, and to be able to identify sources and sinks for that could be kind of difficult, and it's the kind of thing where an LLM can be quite powerful. So that's where we're getting a lot of the value from this. I think that's what we'll discover as we continue to read through the paper. So, and then if you, just for fun, what I always like to do, let's just look at some examples. This is just a bunch of malware. So if you click on any of these repos, it's a repo for some malware, and they show you, they have pre-detected already certain flows you're supposed to find. And you can also see the number of classes and methods and the code complexity here. And same for, what's this other one? Let's see, Juliet test suite. Let's just take a look, see what this is. An example from the Juliet test suite. Great, so you can see that. You can see Taint Bench. Okay, let's move on. Okay, so now that you've taken a look at the data set, now let's look at the results. Let's see maybe how, let's take a look at how LLMFDA does. Let's take a look at how the prior state of the art does. And then if we have time, we can look and dig into what they're doing to get there. So here we've got some results. This is what we actually wanted to see. Okay, so here you can see the results on the Juliet. Results on Juliet compared to a few other models. And you can see here, so what are those models? Code Fuse Query is one of them, and the other one, Pinpoint, and LLM end-to-end. So what does that mean? Code Fuse Query is one model we're using. Code Fuse Query, what is it? Compilation. No compilation. So that's a cool thing about Code Fuse Query. So Dataflow from AST. Pinpoint requires compilation. So a little slower to run. We expect that to be a little better. Pinpoint's the yellow one, so you can see high precision, but lower recall. So we miss more with that, and let's see what that is. So, okay, the problem with Pinpoint misses lots of sources and sinks. So the way they say, due to lack of comprehensive modeling and customized support for source of sink, it can miss stuff. So that's sort of this. Those are this other state-of-the-art models. We don't need to become experts. We don't really need to understand exactly how those work, but you can see where they're falling apart. You can also see here, and this is like kind of the core of the paper, really. This green one is the interesting one, LLM end-to-end. And what that means is like, hey, let's just pretend you're trying to do this and you didn't write this paper. Like, let's just say you want to make a code flow machine in the stupidest, most straightforward way possible. So you might just write basically a prompt like this. So you might write a prompt something like this. In the paper, it's a little more complicated, but this is basically the idea of it. User, here is the program. Here are all the lines. Please detect the bugs in the program. And they use chain of thought reasoning, so you can see, some example here in their prompt. So it's just sort of, if you only use the LLM and you just ask the LLM as of early 2024, when this paper was written, like, hey, can you find these bugs? It doesn't perform great. You can see these green lines here. So particularly low precision for almost everything compared to all the other models. And, decent recall, but still not always great, and certainly not as good as our top tier model for DBZ. So how do they improve on that? All right, so now the real question, how do they do it? What are they doing besides just querying the LLM? So we talked about their method much earlier. Source sync extraction, just find the sources and syncs, Dataflow summarization, and path feasibility validation. So some of those things the LLMs are really good at, and they just let the LLM do that stuff. Some of those things the LLM is less good at, but there are other really good, just off-the-shelf existing tools that do it. So they let the good tools do what they're good at, and they let the LLM does what it is good at. Okay, well, how do they say this? Extracting sources and syncs is non-trivial with LLMs. Makes sense. It's expensive. You have to run all your code through it, and you get some hallucinations. So instead, what do? They use the LLM to synthesize script programs using parsing libraries as source sync extractors. So in other words, instead of having the LLM detect sources and syncs, which it's not good at, they use the LLM to write a program that could detect sources and syncs, which is nice because that way you can just tell the LLM, like, hey, write me a program to find divide by zero lines where potentially someone could divide by zero. You can give it examples. You can do few shot examples to help it out as it's writing its program. So they automatically write a source sync extractor. The other really powerful thing about that, especially for Taint Bench, is that it allows them to detect all kinds of errors that were not of those three classes we set earlier. So if you want to build like a personal information leak detector, you can do that with the LLM without having to go write a custom detector for each kind of problem. Okay, the second thing that they do is Dataflow summarization. So this idea of, like we talked about very early on, how do you connect this input X to this B variable here? And that, I believe they do with the LLM. I think they say they write a few shot prompt. So offering few shot examples with detailed explanations can expose typical patterns of data flow facts. So I believe they just were able to prompt this using few shot examples. In other words, giving it several lines of code, a line of code, an example saying, hey, these two variables are connected, and just giving a bunch of examples like that, and then giving it a new block of code and asking, are these two variables connected? Okay, the final step of this is being able to determine, okay, now we know sort of in code, like this variable on this line is connected to this other variable on this line. We've confirmed that. But we now need to know, is there actually a viable code path that would trigger the bug we're trying to detect? Or has there already been enough if cases or control flow stuff that it can't happen? So apparently that's very hard for the LLM to reason about, or at least at the time this paper was written. So at the time it was hard. It's possible that O1 can do a better job of it. But even if it can, it might be a little expensive. So what they do is they use a constraint satisfaction solver, which is a program you can run. So you can take a look at it here. You give it a list of constraints, and it will solve those constraints. Say, is there a way for all these things to be true at once? And that's the kind of thing that you can, you sort of want to do that here and say, is it theoretically possible for B to be greater? So let's, in our constraint solving problem is B is greater than 1 and B is 0 and, B is going to a sink. And I guess X and B are the same thing. If all of those are true or potentially true, we have a potential divide by 0 bug here. If any one of those is not true, then we don't have a bug. So constraint solvers are really good at solving that sort of thing. And the way they do it here is they ask the LLM to write the constraint problem. So they give it the code, they give it whatever they learned so far about the Dataflow path, and some rules about the problem they're trying to solve. For example, if it's a DBZ problem, then you need to check that your sink is going to be not 0, essentially. And then you tell it, hey, write a program for Z3 to validate it. So then the LLM automatically writes a program like this, and then you go run that in Z3, you get your constraint checks, and you find your bugs. So the really critical part of all this is we're using Z3 to do constraint solving so that we're not asking the LLM to run code, which it's not good at. And we're also not asking the LLM to analyze the abstract syntax tree and find sinks. We're asking it to write code to do that because it's cheaper and it works better that way. And that's it. And then when you do that stuff, you have a pretty effective way of finding control flow problems.